Okay, so our first speaker is Peter. He will give the talk on the topic of topology preserving. Okay, and introduction. As my name is Jázmin Szörfi from Shapers 3D, and also my colleagues Márton Vaitkus and Tamás Várady. So, sorry. Yeah. Let me give you some motivation first. This is about polyhedral design, and polyhedral design is usually associated with the recursive subdivision. So, for example, Catmull-Clark or Do-Sabin. But these methods are not really applicable when the polyhedron has faces that are concave or have internal holes. So, for example, Catmull-Clark uses the face centroids to create new vertices, and Do-Sabin shrinks the faces. So this makes these procedures hard to use when you have concave faces or holes. And what is normally done is that these complex faces are subdivided into triangles or a collection of triangular and quadrilateral faces. But these kind of decompositions are ambiguous and may create high valence vertices that diminish the quality of the surface. But there is another approach to polyhedral design, which is to create surfaces directly by first creating a curved network. This curved network can have various topologies. It can be dual, so a vertex is associated with a surface and an original face is associated with a vertex. Or it can be like a single Do-Sabin step, so vertices and edges are associated with surfaces. Or it can be topology preserving. So vertices are associated with vertices, edges with edges, or curves, and faces with surfaces. So we will look at topology preserving method today. And the interesting thing is that we will use a single multi-sided surface to create these patches. This has been done before, so there are various methods in the literature that do something similar. Especially, I would select this one. This is the S-patch, a very early and prolific example, which is both a dual and topology preserving method. But neither of these methods can do concave faces or internal holes. So this is where our paper comes in. Our goal is to create a polyhedral design method where we allow polyhedra that contain faces that are concave and can contain internal holes. And to do this, we have a very simple workflow. In the first step, we have the simple polyhedron, and we create an auxiliary polyhedron from that by doing some kind of chamfering process. And for this, we actually just shrink the faces and then connect the vertices to create a topology similar to a Do-Sabin step. And then we can see that we have these extra faces. And from these faces, we can create ribbons that will give us the boundary information for creating surfaces later. So each edge of the original polyhedron is associated with a pair of ribbons, and this pair of ribbons is created in such a way that they are G1 compatible. And when we have these ribbons, we can create the surfaces, and we are done. So this is the general workflow, and let's see how this is done in detail. So the first real step is to create the auxiliary polyhedron, and as I said, it's like shrinking the faces. And this shrinking is done by a kind of offsetting procedure. So for example, if we look at this left pink edge here, we try to push it in the normal direction and see how far it can go. And we can see that it can go as far as the dotted line there because it meets this vertex there. And we say that the maximal offset distance is half of this distance, so it's this distance shown in the dashed line. The same can be done for all of the edges. An interesting example is the red one on the bottom, because now you can see that we are only interested in this wedge region shown in red, which is defined by the adjacent edges. So the maximal offset distance will be this dashed line there. When we have these maximal offsets computed, we use a fraction of these, some percentage, like 70%, to create the actual shrunken face. So in this case, for 70%, we have this yellow polygon. And note that the concave corners are replaced by segments in this shrunken polygon. So this is how we create the faces, then we connect these vertices, and we get the auxiliary polyhedron. In the case of a cube, the auxiliary polyhedron looks like that one. And note that for each edge, we have a surface, and the two vertices at the ends, we also have one surface each. And these three surfaces will be used to define a pair of ribbons. And this is shown in a schematic diagram here. So you can see that the ribbons are actually cubic bilinear Bézier surfaces, and their control points are placed on the corners, edge midpoints, and centroids of these faces. But if we create these Bézier surfaces like this, they won't be generally G1 compatible, so we also need to do some scaling and tweaking to make them compatible. But once that is done, we are having two compatible G1 Bézier surfaces, and we only need to do one final step, which is a concatenation. So if we have concave corners in the faces, then the Bézier surfaces around these corners should be concatenated. So in this case, for example, we have 1, 2, 3 Bézier ribbons. And because these two corners are concave, these three ribbons should be concatenated into one B-spline ribbon. And with that, we are done with the ribbon creation process. And finally, when we have our ribbons, these define the outer and inner boundaries and boundary constraints that we want to interpolate. So the final step is to create a surface that does that. And we use, for this purpose, generalized B-spline surface, or GBS. And as we have heard yesterday, these are created by first creating a curved domain based on the boundaries. And also we need some special local parameterizations. For each edge, we have an associated SI side parameter that goes from 0 to 1 as we go along the edge, and also an HI height parameter that goes from 0 on the base side to 1 as we reach the far sides. And when we have these local parameterizations, we can look at the patch equation, which is just a weighted sum of the control points, where the weight is given by a B-spline basis function, by the side parameter, Bézier or Bernstein basis function on the height parameter, and also a rational scaling function. And with this, we get a simple surface that can optionally contain also holes. So this is our whole process. And let me give you some details about the construction, which I think are interesting. So first, I have told you that we only use a percentage of the total maximum offset distance. And this is actually a parameter that you can use for controlling the fullness of the patch. So using larger values will give you more smooth corners and edges, while using lower values will give you a more tightly blended appearance. Also, as for the patch quality, this patch is G1 algebraically, but numerically it's almost G2. So you can see that the isofault lines go through the patch boundaries very smoothly. If you compare it with subdivision, it's a very different kind of patch than Cotmore Clark or Do Sabin. It's hard to say which is better or worse. It is a different kind of appearance. We have also experimented with alternative chamfering methods like fixed offsets or edge symmetric offsets, and also with alternative patches like the biharmonic patch, which is a discrete patch type, which minimizes the seam plate energy. But we have found that no matter which type of patch you use, the result is very, very similar. So this is not a really huge difference. So to conclude, I've shown you that we have done a topology-preserving surfacing method that can handle multi-sided, concave, multiply connected faces, and it is based on a simple offsetting process and uses generalized B-spline surfaces to create the actual patches. And in the future, we may extend this to allow open control meshes, maybe G2 continuity, and optimize domain mapping and so on. So thank you for your attention. Yeah. This one? This one? Uh, oh, this one. Okay, 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 okay. I see. Uh, which one? The red one? The red line. This. Yeah. Yeah. Okay, so you only care about this wedge region, so the square does not go into the wedge region, so it's not. Yeah. Okay. Okay, maybe. Yeah, probably, yes. The red region is very simple to define. You just take the adjacent edges and intersect.
Okay, thank you for the introduction. So in this work, we talk about a novel framework that takes structural, like stress-driven or user-defined inputs to generate Pythagorean-Hodograph curves for additive manufacturing. So while pH curves are widely used in CNC machining and robotic path planning, so it has not been adapted for additive manufacturing so far. So there is only one work done by a group, but it has some limitations. So this is a machine part which pH curves are used, and you can see the surface quality here compared to the linear or circular G-code approximation. So why we choose pH curves or standard representations? Standard Bézier and NURBS curves lack an exact algebraic arc-length parameterization. So this is sigma. It's a parametric speed for the curves. So this is a polynomial so that we can exactly calculate the arc length of a curve. That's why they use it in subtractive manufacturing. So because CNC machining shares same framework with additive manufacturing, we think that maybe it can be used for AM as well. Therefore, we try to leverage these advantages in additive manufacturing. So in prior work, which we done with my student, which is over there, so our YouTube influencer. So he used it for support design, two-dimensional support design, but it's limited to 2D pH curves. So we want to extend it for fully 3D multi-axis print pads. Here's a table summarizing the outperformance of these curves over Bézier and linear segments. So they offer exact algebraic arc length, low G-code interpolation costs, and exact curvature calculation, which is also important for discretization, and also significant lower data storage systems. So here's proposed workflow. So we begin with a tetrahedral mesh. Of course, we can use hex meshes as well. And then we define a guiding vector field. It can be either coming from FEM simulations or it can be even user-defined. And we optimize this field. So actually, we mostly inspire this work from reinforced FTM by Guoxin is here and also Zichin is there. So it's their work, also Charlie's work. But we slightly modify some parts of these methods. So from these optimized method, we extract isosurfaces and we get intersections. And finally, we obtain target points and also tangents, which we are going to use them for pH curve fitting. So here is the input. So it's a Hermit data where we want to satisfy positional and tangent constraints first. So to encounter the high computational cost of exact fitting, so this is coarsely sampled actually. So if we use this, yes, we can obtain pH curves, but instead we try to simplify it, simplify the Hermit data. We use hybrid Douglas-Pecker simplification method. So you see some blanks here. So it means that we already simplify it. And then we use an incremental greedy pH fitting algorithm. So then we can obtain pH curves. So once we have a set of pH curves, we have a G-code interpolator dedicated to pH curves. And then we discretize these pH curves using exact arc length property and curvature calculations of them. And finally, we export a G-code for a given set of pH curves. So we validated our results using our different models. So there's an FEM boundary conditions for a hand model. So on the top left, so you see the print pads, pH print pads are elongated along the maximum principal curvature directions. And on the top right, you see black arrows, which are the user-defined constraints. So that can be satisfied and elongated along these constraints. And also we validated these models using our lab's 5-axis simulator. So we track the dynamic orientation of the extruded cone, like this represent the yellow cone represented. So you can see it changes its movement orientation along the pH curves and tries to deposit the material as much as vertical possible. And also we fabricated those models using our actually use 3-axis here, but it's a 5-axis. It is a manufacturing machine, and confirm the surface quality of those printed models. Okay, thank you very much for your attention. Can use some compression tests, some stencil tests, this mechanical processes. Actually, this has been already studied very well by Xing and Zichun. So this is a somewhat, so we try to use a novel curves and try to exploit their nice properties. However, we also validated at the end of the paper that one of the reviewer asked, is it you? I'm not sure, but okay. So he asked that why don't you validate this property whether it's still satisfied? So we saw that when we follow the stress maximum principal stress directions, so it's stronger than that of the other printed parts like planar printing. So we already validated them. Yeah, yeah. Yeah.
Good afternoon, everyone. My name is Chuanzhao from Beihang University, and today I will present an efficient T-spline surface skinning method via the inverse Bézier extraction. Here's a quick outline of the talk. Surface skinning builds a surface from a set of cross-sectional curves and is widely used in CAD for freeform shapes such as turbine blades, ship hulls, and aircraft bodies. The classical approach relies on NURBS, but NURBS requires all the curves to share a common knot vector, which introduces numerous redundant extra control points. These limitations are what motivated the development of T-splines. By allowing T-junctions, T-splines support local refinement, which makes them a natural fit for skinning problem. Two T-spline skinning methods already exist. Nasri and colleagues separated each pair of adjacent curves with a single intermediate curve, so that each curve can be interpolated locally. O and his colleagues instead add two intermediate curves to preserve shape, but both of them introduce intermediate curves, which add extra control points and don't fully exploit the flexibility of T-splines. And this is exactly what our method sets out to address. We propose a new T-spline skinning method that improves data efficiency and offers a general systematic modeling procedure. So here's the idea behind our method. We call Bézier extraction in the forward direction. Each T-spline element maps to a Bézier patch through an extraction operator CE. And our key idea is to run this the other way around. Instead of starting from the T-splines, we build the Bézier patches directly from the input curves, and then obtain the T-spline control points through the inverse Bézier extraction. The method has 4 steps, which I will go through one by one. Step 1 is a pre-image. We take the union of the knot vectors of all the input curves, and from each unique knot, we extend a horizontal edge toward the neighboring curves. Since all T-junctions lie along the skinning direction, the resulting T-mesh is analyzed suitable, which means the extraction operator is full rank and therefore invertible. In step 2, we construct the initial Bézier patches using cubic Hermite interpolation. After pairwise knot unification, the curves give matched Bézier segments. The boundary control points come directly from these segments, while the interior ones come from the tangents along the skinning direction. So the shape is controlled through these tangents, and different choices yield different surface shapes. We provide 2 options here, a simple difference scheme and a Bézier tangent method that uses both neighbors. Step 3 is the key step, enforcing C2 compatibility between the patches. Since our target is a bicubic T-spline surface, adjacent Bézier patches have to meet with C2 continuity across every shared boundaries. Consider a local T-junction Consider a local T-junction with three patches, S1, S1, S2, and S3, sharing one common cross-sectional curve, as you can see here. We then need three conditions: C2 between S1 and S2 along the U direction, and C2 between S1 and S3, and between S2 and S3 along the V direction. This is the C2 condition between S1 and S3 along the V direction. The control rows of S1 are given by this matrix M13, as you can see here, which depends only on the scaling ratio eta. So we get an explicit formula for S1 directly in terms of S3. And the condition between S2 and S3 takes exactly the same form as you can see here, only the matrix changes. Another result concerns the U direction. The two V direction conditions already fully determine all the continuity degrees of freedom, leaving no freedom in the U direction. Yet the C2 condition between S1 and S2 is still satisfied automatically. We prove this by substituting the V direction conditions to the U direction requirement, which is then satisfied identically. So it never has to be imposed separately. In step 4, we determine the T-spline control points, element by element. PE equals CE inverse transpose times BE. The shared control points computed independently from different elements are numerically consistent, so they combine into a single valid global T-mesh. And we have demonstrated some examples here. Now let's look at the results. We start from four curves with common nodes, and then modify the interior nodes slightly. Our method reproduces the surface, and the geometric difference from the reference nerve surface stays within an acceptable range, which confirms that the construction is stable under node perturbation. Here is the efficiency comparison. On three industrial models, a Naka airfoil and a shape hole and a turbine blade, our method constantly uses the fewer control points. Compared with nerve skinning, we save 26-28%. Compared with Nasser's method, 19-29%. And compared with O's method, 51-62%. Since we avoid the intermediate curves entirely, our representation is thus far more compact. And the method also gives practical shape control through the choice of tangent. Here, the curves and the pre-image are identical, and only the tangent changes. On this facial model, the different scheme leaves small bumps around the nose area, as you can see here. And whereas the Bézier tangent gives noticeably smoother transitions, as you can see here. So the user can trade off locality against the smoothness simply by choosing the tangent. The construction also stays robust under strong variation along the skinning path, keeping a good overall shape under the large progressive and helical changes as shown here. Finally, mixed continuity skinning, some designs in the sharp crease at a particular section. We can allow C0 continuity along the skinning direction at selected sections. The rest of the procedure stays the same, and the creases reproduce the intended shape as you can see on the lamp and the rook models. Finally, to conclude, we have presented a T-spline skinning method based on inverse Bézier extraction. One that uses no intermediate curves. We derive the interpatch C2 conditions analytically. The method gives shape control through the tangents and produces a compact T-mesh with fewer control points. With its efficiency and generality, we believe it has strong potential to become a standard approach for T-spline surface skinning. For future work, we plan to extend the method to periodic curves. Beyond that, since the inverse Bézier extraction naturally merges several patches into a single T-splines, so it's well suited to trim nerve surfaces. We therefore aim to construct watertight T-splines from trimmed nerves models, bridging complex CAD models to isogeometric analysis. Thank you for your attention, and I'll be happy to take any questions.
Maybe I just ask one. I see the velocity of one is very sharp angles. Yeah, this one. The C.
Okay.
How does this compare with conventional results?
Compare with what?
With the graphics of this one.
So you mean the
You mean how your method can combine those really sharp corners?
This actually is not a sharp. It looks like a sharp shape, but actually it's still C2 continuity. During the you think it's sharp, but in numerically it's C2 continuity. Yes.
Oh. Any other question? If not, a central figure. It's representing itself.
You have the little dongle there that
Yes.
adjusts to this. Perfect. Oh, yeah. We need that one, I think. But if you give it to me, I'll just stick it.
No, what if boundaries and in the small slide surfaces with shortening vertices? Switch. That is good.
Yeah, this looks good. Thank you very much.
Yes, this one.
There we go. All right. So this is about boundaries and creases in the context of extraordinary vertices. If we don't have extraordinary vertices on the boundaries on the creases, this is not a very interesting story. This is joint work with Param Gupta, my student, and Kestutis Xiaoxiao in the background. So what's the story about? So let's assume we have some really high-end freeform spline surface, and the high-end means that has nice reflection lines, it has nice mean curvature distribution, everything is curvature continuous. It's a quite complicated scheme that you don't want to reinvent and modify. You just want to use it as is. For example, you could choose something like polysplines or whatever it is. But then someone comes in and says, hey, we can already do all these great things using subdivision, generalized subdivision, Cutmore-Clark with bells and whistles. And in fact, most commercial packages have something. Sorry? All right. So what they have is all these packages, and there are many more that I list here. They have taken so-called Pixar boundary rules and sharp darts and whatnot. So they have a whole collection of rules that do special things that designers have become accustomed to. It's not necessary that these are the best rules, but these are the established rules. And now the question is, how can we take something like this that's a high-end, looks good, and impose a good number of these rules to that without reinventing the code? So as few changes as possible. This is for lazy people like me. Now, there's one thing with the Pixar boundary rules that is unfortunate, but it's the rule. There's something called the global boundary polygon, and I've chosen here a mesh that's really small, 4 by 4. Now, think of it as being much larger, but it has a global boundary, and it has a corresponding polygon, global boundary polygon. What the Pixar rules say is not only does this global boundary polygon contribute to the surface, which obviously it does, you see here by cubic, right? Those of you who are familiar with that, but it has a second role. It also defines a boundary curve just by being the polygon. I'm not saying polyhedron, I'm saying polygon. The polygon also traces out a space curve, and they want this to be interpolated. So 2 roles for the global boundary polygon. And that means you actually have to invent a surface that goes between the green and the red. And subdivision does that because they have infinitely many pieces to work with, but we have a finite surface scheme. So we want to have, in short, Pixar-like boundaries for these high-end surfaces. And why do we want to have that? Well, people stick pieces together. So for example, this here, it might be for your coffee dispenser, it's the handle, and you want to snap it together with other plastic parts. You want the exact same boundary, or maybe epsilon offset, but you want to have exact control over it. Second thing is the creases, is because on this arrowhead, for example, you want to have a sharp edge that then becomes something more rounded. And most of all, you want to be lazy and avoid new rules. And then one variable, we already know what is to be done. If you have a cubic spline, you stop before you come to the end. You lose sort of a little bit. You evaluate where there's enough B-splines available. And that means that you are shortening the curve vis-a-vis the control net. If everyone would adopt that rule, we'd be done. We don't need this talk here. This is, to me, the sensible and natural rule. Seven called it the truncated rule. Now, in the curve case, we can either work in the domain, and we have singularities in the domain which are called multiple knots, and we have de Boer's algorithm to take care of these singularities. Or we can go into the range and have multiple control points. This is taken care of mathematically by Orbital's rule. So now going to surfaces with extraordinary vertices, we have again input from Markham Sabin and his co-workers, and there's the truncation, which we already defined. And now let's again look at what's happening in the domain. Let's say we have this multi-sided facet. We don't know what it means to have multiple knots in such a multifaceted environment. Now, there are some ways and means to invent multiple knots, but it's certainly not convenient, and there is no such implementation at the moment. So we don't quite know how to do this in the domain. So in the range, what can we do? We can play with Bézier coefficients. Markham was recommending at the boundaries, but that's special new rules. We don't want that. There's another one that's combined subdivision by Adi Levin, where we are getting closer and closer to some prescribed curve, which need not be the global boundary polygon curve, but can be any curve. But that depends decidedly on the fact that we have an infinite number of pieces. And this is what I want to use. I can again use L'Hopital's rule. That means control points on top of control points, which means I have some derivative differences that become zero, but we know what to do with that. We need to look at the next layer of differences. Here's an example of a challenge. Obviously a box. Red is interior. It's not connected. It's not a surface. It's the interior of the back. Blue is the outside. What I've done here is I've taken a quarter of one of the panels and removed it. So I now have in this red, there's actually a boundary vertex that has 4 neighbors, and 4 on the boundary is irregular. 3 on the boundary is regular. Obvious? Good. And this is what subdivision returns. Actually, it's cheating. It shows you this here, but what's really happening in the vicinity of this point is an infinite sequence of nested rings that converge towards this multi-sided point. So, but this is what people say is the standard, and you have to replicate it. This has to do with the B-rep. Their B-rep says this is one piece here. In fact, it's an infinite number of polynomial pieces. And now you can look at the paper, and there's rule 1, rule 2, all smart ideas. The interesting contribution of this here, I'm making it into a movie. The interesting contribution is, I think these are all the ways that you can be lazy. These are the 3 options you have to not invent new rules, but simply do a change of your control net to give you boundary rules so that you can do almost what you can do with sub-D, meaning some of the sub-D are just cannot be replicated because they depend on infinitely many pieces. But they certainly look alike. In fact, they interpolate the same global boundary curve. And here's the little table of what you want to do. The last one is reliable kernel support. And there we see that one of these doesn't, one of these doesn't work properly. What is that? That is a double singularity which parasolid the underlying kernel of, in this case, plasticity is based on that. The underlying kernel cannot handle double degeneracies. That's just, they haven't implemented all of L'Hopital's rule. Okay, and then you have different rules where you have either corners rounded or corners smoothed. Okay, last part, creases. There's an easy way to do creases. In fact, there's a super easy one, is cut your object apart, use the boundary rules that interpolate the global boundary curve, and have them to 2 parts have the same global boundary curve. Now you can stick them together and you have something sharp. But that's really bad because you just broke the topology of the object. And if you ever wanted to smooth it out again, you actually have to have some fusion between the pieces. So here are again the 2 things on the subdivision and the high-end method. This one here is actually, strictly speaking, C1. This one is actually everywhere curvature continuous. And this is when you're sharp. And how do you do that again? Well, you insert mesh lines, and then you can by the same trick as for the boundaries, get this. But this is inserting a whole loop. This is a small object, and I've inserted a whole loop. No problem with that. This is not typically what you want, that you insert everywhere whole loops. Might be a large object, might be a large loop. The second thing that you also want to have is you want to have sharpness, and you want to have semi-sharpness, where this is slightly rounded, and you want to have a continuous family that goes from very sharp to very high curvature as less, and then, but the moment you go away from absolutely sharp, you want to have curvature continuity, even if only with a very high curvature. And again, here's your typical test problem that you would see, say, in a Pixar paper by Tony Rose and company, where you want to insert a sharp crease on an otherwise rounded object, and oops, one back, and there's the semi-sharp crease for in E for subdivision. Looks a little wobbly. I don't know where that comes from, but that's what it produces. And on the right is the same rules now reinvented, but for this finite higher order surfaces. And then the final thing, pièce de résistance, which is actually in some sense the second and important contribution of this, is that you want to stop the sharp crease and you want to pattern it out, make it smooth. This you do by removing your control lines. The red ones are the ones that decide this. And there's a nice control pattern that you get that I can explain offline because I'm likely out of time at this point. Thank you. Sorry to be turning this into a movie, but we want to be on time. Good. All right. Yeah. Angels. Three creases that come together. In this implementation, no. Absolutely not. In fact, it's a very interesting challenge because more things break than you are aware of the moment you have many creases come together at a point, because everyone else who comes into that point will also break their C2 continuity, but you want to preserve it. And so again, the big question is, can you get away with laziness? And that's, so if you can help me with laziness, I beg you, tell me. You don't want to have special rules, special tables. That's not what subdivision has to do. But again, they have an infinite budget. We don't. We have a finite number of polynomial pieces, not an infinite one. Stephanie. The tangent directions across the boundary. Yes. Yeah. So again, all the way along the boundary, you are curvature continuous, and yeah, you just end, right? You're going across. This. One of the question is, would you want to give handles to the user to modify? Yeah, but that would be at the Bézier level that you play with that. Yeah. Yep. Do you also need? Yes. Okay, thank you. So luckily, this morning, Brian talked about subs. I just think, but I will explain it in a different angle. Let me go quickly. One thing Brian didn't mention, the first idea came from Lucas. Like he wrote the equation. Almost Because I sent this papers lots of this we had the same, but Ricky and Nikovsky was he can know what so these colleagues, this is what people and once then came because I journals. I think we often have so I listened to my tutor PhD so I can come and realize this always content. So I can feel like I and then I was able to know that and then of course Brian block the idea and then I can decide almost somewhere but because from more important than because when we part of in this was a I'm going to improve the watching exactly next time I was important and then it was partly on the movements this stuff right now this And then what we must shoot. That means if you have a student that are really trying for them, that you need to find. Something better. You can merge when also so that's my I was over to the one machine is see but if you say why it's because people without so that you like not because you know because I don't know that any day I think the scheme of what someday starting this like that it turns out that why don't you this so so I don't know so stuff is a it was coming up 6 years ago. Oh, I'm starting to think about this. Last year, they didn't want me just because this simple solution. This local was one is how we believe this. Then this she integrated or woman something like that is nice. So one thing is so all it's so very like in one condition. Sure. it shows something this. So continue in the, well, you can see that. I'm doing the many transition, they become big, they become bigger, bigger, bigger. I'm going to use this. Look at this. Look, big. You get this last year. Look at the ground. I think I need yes. Like we can do something. And then the weights effect. So I will do this this. So this paper from us, this paper also from us. Nice. Nice. Something very complicated. It's such a lot of and then you can choose something. So basically, as we said that, we had a box. I didn't think of objects. So I use that kind of stuff. Some patterns really application, computer that have been like this. Each paper. Whether we can do one. I want to solve that but I don't know the word. But the learning problem bottom or weakness is
sharing all the story behind this. I definitely have to check.
and
Yes. Here. Here.
Have you also
Okay. Good afternoon, everyone. I'm Shentong from Zhejiang University, China. It is an honor to present my work at ITU. The topic is MBTC, efficient and accurate Bernstein polynomial composition via monomer basis transformation. Let's formally define the core problem, Bernstein polynomial composition, or BPC. This refers to the operation of composing two Bernstein polynomial functions. The inputs are the inner function g and the outer Péter function f. And our output here, the result is the coefficients vector of the newly composed function rather than just a single evaluated numerical point. BPC is an important fundamental operator in CAD systems, widely used for modeling and processing of parametric curves, surfaces, and volumes, such as representing P-curve on trimming, FFD, and the modeling of microstructure. And improvement in its performance yields benefits for all downstream applications. For such a fundamental operator, numerical stability, high efficiency, and ease of implementation are crucial. But existing methods face trade-offs in achieving all of them. Reviewing the existing method, the product and Blossoming-based method ensures good numerical stability via convex combinations, but heavy relies on recursion and linear combinations, which make it inefficient and hard to implement, especially in higher order and dimensions. On the contrary, the interpolation method is highly efficient and easy to implement using matrix operations, but, but it serves from poor numerical stability due to a large metric element. Finally, uh, symbolic rational computation provides machine precision, but its efficiency is much lower. To further improve efficiency and resolve the trade-offs, we propose MBTC. In the first step, we convert the coefficient vectors of the input Bernstein polynomials g and f into the monomial basis, or we said power basis, via a linear transformation, which is formulated as a matrix vector multiplication using the basis transformation matrix. Next, compute the functional composition in honors form under the monomial basis. The honor composition in this step is different from the standard honor evaluation. Instead, it makes use of the honor structure to perform exact coefficient composition. Finally, convert the results back into the Bernstein basis. This measure, uh, this method straightforwardly principle leads to easy implementation and adaptable to various geometric representation, include curve and high dimensioned simplexes and tensor products. It delivers high efficiency than existing methods while maintaining acceptable numerical stability. understand why MBTC is so fast, we divide the time complexity in two modules. Let's break down. First, the basis transformation. The time complexity of this module is always a minor term compared to the composition itself. And as a linear transformation, the transformation matrix is constant. And it's a constant matrix for fixed degree and forms, and it can be pre-computed offline. Furthermore, when dealing with tensor product surfaces, we can compute this transformation respectively along each parametric direction, which further optimize the performance. For the honor composition module, honor method can reduce redundant computation and make it faster than the direct polynomial expansion in the power basis. Although some power composition algorithms have a lower time complexity than honors, but we choose honors for a practical reason. Experiments show that in common CAD scenarios, honors method has a clear advantage in its constant factor. Other advanced algorithms only perform better at extremely high degrees. Finally, taking the curve case as an example, the dominant term of MTTC's time complexity is always the smallest among all methods. Here, the D means denotes the degree of input function. This page we talk about the numerical stability. First, the basis transformation module. The numerical risk comes mainly from the Bernstein to polynomial forward transformation, where non-zero matrix elements are greater than or equal to 1, amplifying rounding errors during the multiplication. Conversely, the inverse transformation has elements between 0 and 1, which does not amplify errors. You can look at the two matrices. So because composition uniquely takes low degree input and yields high degree output, the risky forward transformation is strictly limited to low degrees, while the high degree inverse transformation remains stable. Second, the honor composition module reduces the number of operations, minimizing error. But what about Vaitkus' famous destruct of the stability of power bases? We have two responses. First, his conclusions focused on the root solving, but not coefficient composition. They are fundamentally different. Second, Vaitkus argued that large condition number of transformation matrices cause unstable. However, the condition numbers measure relative error. It terms of relative error, even stable convex combinations lose significant digits due to catastrophic cancellation. The cancellation, if the input itself is ill-conditioned. To truly evaluate the process stability, we should look at the absolute error, the amplification of rounding errors. From this perspective, our theory is reasonable. This table shows the runtime and significant digits for several respective scenarios. Looking at the here, The CC stand for curve on curve, and TC stand for curve on tensor product. A TT means tensor product on tensor product. The numbers in the brackets means the degree of the inner function, outer function, and compose the result. Looking at first at efficiency. For basic cubic Bézier curves, all methods have similar runtimes. However, as degrees and the complexity of form increase, MBTC shows a growing efficiency advantage. The second table shows the significant digits. The symmetrical Guoxin method lose the fewest digits. Meanwhile, MBTC similarly to the product and the optimal Guoxin method, and is much better than the interpolation method. These experimental results are consistent with our theoretical analysis. In conclusion, we propose a new method of BPC applicable to arbitrary degrees and dimensions for both simplex and tensor product forms, which achieve the optimal efficiency while maintain adequate numerical stability, resolve the trade-off between speed and accuracy. Finally, it has a simple structure and is easy to implement. That's all. Thank you for listening. Table? Sorry? Uh, this table. You can see the sorry, I don't understand your no parallel computing, no parallel computing. Okay, thank you for your question. Um, it's a okay. We actually explored other bases, such as chapter basis. However, we didn't include this in the paper because our experiments and analysis aren't enough yet. But currently, we see two main drawbacks to other bases. First, the numerical cost of the basic transformation is higher than power bases. Second, the computation, uh, the the the, the operation itself is not as straightforward as it's on the power basis. So we chose the power base now. Yes. 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 Thank you very much.
Hi everyone, my name is Sheng from Zhejiang University. Today I will present our work on PDH cat. As we know, modern AI methods have shown strong potential for cat modeling, but high quality cat data is much harder to collect than images or text. So in this work, we asked, can we combine data-driven learning with explicit cat knowledge so that cat models can be learned more effectively on data scarcity? The presentation is divided into 4 parts, and the first one is the motivation of cat learning under data scarcity. Let me start with the broader background. Intelligent cat is becoming a clear trend in both industry and academia. The industry companies like Autodesk are exploring workflows that turn images or other inputs into 3D models. In academia, many recent works study text-to-CAD or image-to-CAD. This shows a strong opportunity. AI may help automate CAD modeling workflows and make design much more accessible. But the major bottleneck of CAD learning is data. Most learning-based methods require large-scale data. However, large-scale real-world label CAD data is still very limited. Some datasets are closer to real design data, like Fusion 360 or TMCAD, but still small. On the other hand, some datasets have large-scale models, but are usually synthetic data, which cannot be used in real practice. A common response to data scarcity is dataset scaling. They do this by either collecting amateur models or synthetic generation. Both produce unrealistic models. In fact, we may have to admit that small dataset is an inherent issue in CAD. In a specific industry, for example, the number of real product types or design variants is often limited to hundreds, not millions. In addition, high-quality CAD data is usually proprietary and commercially variable, so companies are unlikely to release them publicly. Since rapidly building a large-scale label CAD dataset is difficult, we want to use the function model as a source of knowledge so that we don't really need to scaling data. These foundation models have already shown strong capability in general knowledge domains. The goal is to compensate for the missing knowledge that cannot be obtained by directly scaling CAD datasets. This is similar to virtual scaling. We use the prior knowledge in foundation model to compensate for the required data in scaling, so that we don't really need to do data scaling, but have the same results. This slide shows the overall framework. Foundation models contain broad general knowledge and also some partial CAD-related knowledge. For example, they may answer simple CAD questions, but they are still unreliable for detailed CAD reasoning. We view the knowledge inside foundation models as incomplete in 3 ways. First, some CAD knowledge is weakly expressed or even mixed with massive general knowledge, so it needs to be elicited. Second, some knowledge is missing, especially for really appearing parts or domain-specific components, so it needs completion. Third, there can be a mismatch between the concept in foundation models and the geometry in real practice, because textbooks often show standard examples, while real CAD datasets contain much larger geometric variations. This requires calibration. Our framework combines foundation models, textbooks, and CAD datasets. The goal is to elicit, complete, and calibrate CAD knowledge so that foundation models can be used for CAD learning under data scarcity. The design network contains two components. Component stage 1 focuses on non-eliciting and computation. It extracts that knowledge from textbooks and represents it in the Latin space through a VOM, a large foundation model. And stage 2 focuses on knowledge calibration. It adapts the explicit knowledge, which is a Latin, to the target data set and aligns it with the cat model embeddings. In step 1, we elicit and complete the partial cat knowledge by utilizing textbooks. First, engineering textbooks are structured into knowledge triplets, specifically designed data structure for representing textbooks, also using a VOM. Each triplet contains canonical terminology, description, and visual demonstrations. Then, both the knowledge triplets and cat model views are encoded by a VOM encoder, which gives us data embedding in the latent space. The goal of this stage is to represent external cat knowledge in the foundation model in the latent space of a VOM. Stage 2 calibrates the extracted knowledge to the pocket cat distribution. The shifted vector model adapts category level knowledge embeddings towards the target dataset. Then through cross-attention, we align the concept level knowledge in the foundation model and the geometric variations in small dataset. The experiments evaluate KDH cat and part classification and retrieval tasks. We use cat and fabric datasets and compare KDH cat with some representative cat learning baselines, including UniNet, AGNet, BREFNet, and BRT. The results show that KDH cat achieves higher accuracy even with limited training data. On TM-cat dataset, it reaches 95.8% accuracy with only 1,000 cat data. Performance is also stable across different random splits, which indicates that the method is robust and not dependent on a specific data section. Here we compare KDH cat with baseline models on TM-cat in the February. The main result is that KDH cat achieves sought-out performance with only about 10% of the training data required by those baseline models. We also evaluate KDH cat on the downstream part retrieval task. KDH achieved the same performance with only 1,000 training models, while the baseline models use more than 10 kilograms models. The retrieval results show that KDH cat can learn better cat representations than baseline models. To conclude, this work solves the data scarcity problem from a totally new perspective. That is, can we use prior knowledge in foundation models to replace the need for raw cat data? And our implementation and results show that this is very promising, and we have achieved sought-out performance with only 200 or even 300 data points, which is frankly much better than what we thought at the beginning of the project. In the future, we would like to extend this framework to more downstream cat tasks such as feature recognition and cat model generation. Thank you for your time.